Hi guys, thanks for stopping back to Pete's Garage. We're going to continue on with our engine building series talking about pistons. We'll talk about piston forming, cast, forge, billet, piston materials, piston ring design and location, wrist pin location, the different kinds of coatings on pistons and the different dome designs. We'll talk about the rings, what kind of rings there are, different coatings for rings and the proper installation of all the piston rings, rods, different kind of rods, different materials, different strengths, and installation of a rod with the wrist pin and the keeper, and different fasteners for the cap. Before you put the cap on, you want to make sure you use the proper fastener. Let's get started. We'll start talking about piston design and piston materials. Okay, we'll start talking first about piston materials, about aluminum, the casting versus forging versus billet. Now, the first thing we'll talk about is a cast piston, and the benefit of a cast piston is obvious. It's a molten material, molten aluminum in this case, poured into a mold, and then it's when it comes out of the mold, it's machined to give the finished features like the wrist pin location here, the wrist pin, and all the other different locations are machined to make sure that they're ready for the engine. They are usually designed for a piston location. You can see this one is designed for location piston number 3. That's the way they're designed in sets, and every piston will have an arrow on it which indicates points towards the front of the engine so it's used properly. And we'll talk about dome design in a second. In contrast, you can see a forged piston, and they're two different sizes because they're two different size engines. This is a 4-cylinder engine, this is an 8-cylinder, and a forged piston is a piece of material that's put into a die and then it's heated up and it's forged into the shape, and it has a much more finished looking design. There aren't any casting marks like you see inside a cast piston. And the forged piston has many benefits in the fact that it's a lot stronger. The forged aluminum is has more strength and durability because of the forging, and it has the ability for shape retention. The forged piston is going to retain its shape a lot longer, or a lot more consistency in high performance applications than a cast piston will. And of course, cost is a consideration. Cast pistons can be mass produced very quickly and very inexpensively, whereas a forged piston is a little more expensive to make. Now, they're made out of different materials, and they're mostly aluminum, and you're going to hear something about eutectic pistons, and there's 3 basic types of pistons, eutectic pistons. There's a hypo with an O in it. A hypo eutectic piston is an SAE 332 aluminum, and that will usually contain about 8.5 to 10.5% silicone in there. And what that does is it makes the heat transfer or the heat distribution throughout the piston more even. So the hypoeutectic pistons have a better heat transfer. Then you can move up to a regular eutectic piston. A eutectic piston will have 11 to 12% silicone in it, which will give you better heat transfer throughout the face of the cylinder, or throughout the face of the piston head, and throughout the dome. And then there's hypereutectic with an R, hyper. Hypereutectic pistons will have about 12.5 to over 16% silicone. And the benefit of this is the piston can be made thinner. And you can see how fairly thin this skirt is. So pistons can be made thinner, and with the addition of the silicone will distribute the heat evenly, and will take the heat evenly around the entire piston. Okay, that also results in a reduction of weight of roughly 10%. Now they can take a regular aluminum alloy, and what they will do is they will heat treat it to a T6 aluminum, and the heat treating to T6 will give it roughly about 30% more strength to the piston than just a regular cast piston without being heat treated. Okay? Now, what they've done is they've taken basic piston design, and what has happened over the years is the length of the piston and the parts of the piston. First we have the dome, then we have the side, top ring groove, compression, second ring groove, oil ring groove, and the skirts. And the skirt part of the piston right down here has gotten fairly short. And you can see how short the skirt is on this piston. It's really not that big at all. And they've been able to do that by using different alloys and different materials. And you can see, I'll turn this piston on the side, and I'll turn this piston on the side. And you can see how close the wrist pin has been pushed towards the top of the piston. This distance from the wrist pin to the top is getting very, very short. Now they move that for a couple of different reasons. Moving the wrist pin up allows you to use a longer connection rod. A longer con rod will give you improved torque, and it makes it easier on the bearings and on the piston rings when you have the wrist pin closer to the top of the piston. However, that does cause some problems because you have the distance here between the top ring and the top of the piston does cause some problems for different kinds of distortion, micro welding, and pound out failures from the ring on the top. So what we have is, when we look at this ring groove here, the temperature from the top ring to the top of the piston is going to see about 600 degrees Fahrenheit. By the time we get down to the second ring is going to see about 300 degrees Fahrenheit, and then down to the oil ring it drops down considerably. But when we do this, when we make this here, we get increased risk of cracking for the land failure here. This land can crack, and what they do to try and help that is, if you can see very closely, I'll try and see, you can see that top ring, this top groove here, is anodized. And it's anodized very simply by putting sulfuric acid on aluminum, and they put it in a very controlled fashion. And the sulfuric acid produces an aluminum oxide coating in that ring. And that aluminum oxide coating makes that groove much harder, more durable, and less prone to the groove distortion and micro welding that can occur when you get high temperatures on the dome. Now we look at the side. I have two different pistons here to illustrate something different here. You can see that it's going to be a little difficult. Alright, this piston has a coating on the side, while this piston does not. This piston in higher revolution RPMs, this coating is a graphite moly disulfide coating, and all it does is try to preserve or protect the piston inside the cylinder, so that when the piston is going up and down and it makes contact with the cylinder wall, you get less piston slap and you get a smoother transition with the piston. Now we look at the crown of the piston. You can see these two pistons, they're different shapes. This crown is for a 8-cylinder engine that has only 2 valves, and it has relief cut in there for 2 valves, whereas this piston is made for an engine that has 4 valves in this cylinder. So the relief here is for 4 valves, and the one in the middle is for the spark plug. And the difference in the dome design, the dome or crown of the piston, is designed for a couple things. It's designed for temperature control. You want the hot gases to get out of the cylinder as fast as possible. So the dome design is designed for temperature control. And also these lands on the top of the piston, you see how it's kind of raised there? Those are put there for emission control. If you can control the emissions and how it exits the cylinder into the exhaust, you can control the amount of emissions simply by changing the shape of the land on top. So we look at the crown, and then we also have, which neither one of these pistons have, well, kind of, sort of. These are kind of like a heat groove. These heat grooves on the side, and these heat grooves, which this piston has but this piston does not, these heat grooves are to allow for distortion of the piston. And that's an important factor, because as we look at a piston, if you were to measure this, the piston itself is not round. If we were to look at the bottom here, the piston, if we were to measure it from here to here and then turn it and measure from here to here, they're not different. It's kind of oval shaped. And the reason it's oval shaped is because of the mass of the aluminum. You have different amount of mass of aluminum here versus here, so when it heats up and it expands, it's not going to expand at a constant rate. So when you have more mass, it's not going to expand as fast as it will here, so the piston will be kind of an oval shape. Okay? So when you go to buy your pistons and you think you're going to be buying a perfectly round piston, you're buying a piston that's going to fit your bore, and we'll talk about that in a minute. But you look at the different dome designs and the different shapes, and you can see that obviously for different applications there's going to be different dome designs, different clearances for the valves, and different design for both the wrist pins and the rings themselves. So let's stop right there, and then let's talk about connecting rods, the materials for connecting rods, and what they mean to each piston. So you need to choose a connecting rod, And before you really decide what connecting rod you're going to use, you have to really decide in your rotating assembly for your engine, you need to have an idea of what the engine power goals are going to be. What do you want the engine to do and how is it going to be used? Is it going to be a high revving engine, high revving, high horsepower machine? Is it going to be a daily driver? Do you want low torque? Is it destined for drag racing, autocross, those kind of things? So higher power levels in an engine place increased compressive force. Compressive force is a compression of the rod. And higher RPMs increase the tensile strength. So when you increase the RPMs in the engine, it wants to pull the rod apart. So that's something to consider. And they both go hand in hand because more power requires a beefier or thicker rod. You can see the difference in these rods. This is for a smaller engine. You can see how small this rod is compared to the thickness of this rod. This rod is a heavier rod and it's designed for a high horsepower application. With every rotation of the crankshaft, the rod's going to be alternately compressed and then stretched. So connecting rod failures are usually caused by over-revving the engine. And that replaces a tremendous amount of stress on the rod and the bolts on the bottom. That's where they usually fail. The rod bolts will come apart as the piston travels up. It'll pull down on the bolts. These bolts will get pulled. And the force of the inertia of the rotating assembly will just rip the rod cap. It'll rip this cap right off of there. Rip it right off the connecting rod. If the connecting rod fails because of it, the connecting rod will bend, and this will just blow up your engine. It'll completely seize. And if I have handy here, I do have handy here. I'm going to show you something real quick. Let me grab this. Luckily I have this hidden behind me. Here's a connecting rod that's twisted. If you look at this connecting rod, and this engine failed because of that. The engine was in a high revolution. This is out of a 454 Chevy. It was being tested under high loads and high RPMs, and the rod ultimately failed by twisting, bending on the compression stroke. It was on the upstroke, compressed, blew up, and blew the piston right out the side of the engine. So here's a failure mode for connecting rods if you choose the wrong connecting rod. The I-beam, this design is used in most all production engines, and this is out of a production engine. And the interesting thing about this is, even though this is a cast rod, and this is a forged rod, when you look at the casting here, the cast, this is actually made with cast with the cap on it, so it produces a continuous casting, and it's cracked. The cap is cracked off the bottom, and if you look very close, you can see the material, how it looks like it's cracked. Well, the cap is cracked right off of there, and it's designed that way. It's designed to crack the cap off so that when you put it together, it fits perfectly back together. When you put that cap back on a cracked rod, the seam between the rod and the cap is virtually seamless. You can almost not even see it. So we have the different designs. Here's an I-beam rod, and you can see it's more like an I. The ribs are a little higher, the center's a little shorter, and it kind of looks like an I-beam. If you were to cut it in half, it would look like the letter I. If you're going to use the I-beam rod, it is stronger, and it's going to be used in a high-performance engine, especially with a forged rod. Like this is a forged rod, and this is a cast rod. So there are two different things there. Now, materials for connecting rods. They can be made from various grades of steel, aluminum, and titanium, with steel being the most widely produced of all the types of connecting rods. And these are used mostly for the daily driver, endurance racing due to their strength and the long life, long fatigue life of this kind of rod. The only problem is that using steel rods and this material of steel is very, very heavy, which consumes more power and adds a lot of stress to the rotating assembly of the engine. Performance steel rods, like this one, can be made out of 4340 and even 300M grades of steel. This is a 6250 rod, and the tensile strength, yield strength, and hardness of a 4340 steel depends on the temperature, which is forged, etc., etc. But variations in the tempering and the quenching procedures are extremely different in the rods. This is why it's important to choose your rods and buy your rods from a manufacturer that has very strict controls on their heat treating processes. A 300M steel alloy is much stronger than a 4340, and can be used to manufacture steel rods that are lighter than their 4340 counterparts by using less materials. And 300M rods are rated at the same strength as a 4340 rod, and they can be up from 10 to 25% lighter. Aluminum rods, conversely, are used with used widely in higher horsepower, higher revving engines like a Formula One engine, and higher revving drag racing engines, those kind of things. Aluminum rods can be manufactured to the same strength level as a steel rod due to the large amount of material that makes up the rod, and an aluminum rod can be up to 40% lighter than a steel rod, than a steel connecting rod of the same shape. And reducing the rod reduces the mass. By reducing the mass of the reciprocating assembly, you can get higher RPM, and that's how the whole thing works together. The lighter the weight, the lighter the rotating assembly, the easier it is to move back and forth, so the higher revolutions you can get out of it. You'll get better throttle response out of aluminum than steel, and the lighter weight of the aluminum will reduce vibration and stress on the crankshaft. So the lighter the weight of the connecting rod with an aluminum piston will reduce the fatigue and stress and loading on a connecting rod journal, and it can reduce the stress on the crank. It also can the rods can also stretch, and they may fatigue and fail, but unlike aluminum rods, the modern aluminum are much stronger, and they can be used in daily drivers depending on use of the power level, and they can be 50,000 miles, 60,000 miles before you'd have a problem with it. And the secret of making aluminum rods that last as long as it's not constantly over revving the engine when you drive to work. Aluminum rods are excellent. If you want to spend the money on an aluminum rod, it definitely will last a lot longer. Now, titanium rods are both lighter and stronger than steel, but unfortunately, titanium is extremely expensive, so they're only used in drag racing, endurance racing, very expensive engines that require very, very high performance, very light connecting rods. Unless you're building the ultimate endurance engine, unless you're building it, steel's fine. If you're building an ultimate endurance racing engine, you can use a steel rod. For drag racing, using aluminum rod is both cheaper and lighter, and it's cheaper and lighter than using a titanium. So that's basically the designs and the material considerations when you go to buy the rods. Now, a couple things here we'll just go through real quick about the design of the rod, balancing of the rod, and installing the rod to the piston. Now, if you're going to assemble your connecting rod yourself, which is entirely okay if you want to do that, but when I build a higher performance engine, I have the machine shop do that. And one of the first things the machine shop is going to do is when they match the connecting rod to the piston, they're going to engrave the number in which cylinder it goes in. So it always goes in the same cylinder. They're going to engrave the number on there so you know where to put it and where they matched it for. They're going to stamp it on there, and that's where it should always be placed. Usually right here on the base of the cap, they're going to do that. Now, the machinist, what they're going to do is when they're going to match the components, and they're going to balance each rod. And the connecting rods are balanced on both the big end. On this end they're balanced, and they're balanced on this end. And the reason done this is because they do this is because this end and this end are considered different parts of the rotating assembly. The small end is considered reciprocating weight. This is the reciprocating weight that goes back and forth with the piston, so it's reciprocating. And the bottom half, or the big end of the connecting rod, is considered rotating weight, because this is the part that rotates with the crankshaft. So this is rotating weight. So when they do this, when they balance your rods and they machine them, they're going to balance the rod, they're going to sit it down, and they're going to weigh the tip of the rod, and they're going to balance it this way, and then they're going to sit it, and they're going to balance this side. So they're going to balance both ends of the rods for weight. Those are critical to make sure that the rod is balanced for weight. When you talk about a balanced rotating assembly, the ends of the rods are balanced, meaning the weights of this end and the weights of this end are matched on all the rods so that they're all the same. And then they're matched to a piston location, and the entire assembly is then weighed, and all of the weights of the entire assembly, this entire assembly will be weighed, and any material that needs to be taken off, usually it's taken off the cap end if it's a reciprocating weight differential, or they'll take it off the bottom. But usually when they're manufactured, a forged piston, they're very, very close in weight, and they don't need to be machined for equal weight. So what we'll do is we're talking about connecting rods. So real quick, we'll talk about the different choice and applications. Steel H-beam rod is usually going to be often in low horsepower, 600 horsepower max and up to 8,000 RPM. It can be used for racing, daily driving, those kind of things. Eagle H-beam rods are best for the price, and they're known for their durability. An I-beam rod, this is a cast I-beam rod. However, I-beam rods, moderate horsepower, 900 horsepower max. If you get a billet rod, you can go up to 1,200 horsepower, and moderate RPM, maybe 9,500 to 10,000 RPM for a steel I-beam rod, and suitable for regular driver, endurance racing, and drag racing, those kind of things. If you're looking for that kind of rod, Powder and Crower make the highest quality steel I-beam rods for that kind of application. Aluminum rods. I don't have an aluminum rod because they're expensive. I don't have an application right now, but they're used in high horsepower applications. An aluminum rod can be used up to 1,200 horsepower, and sometimes RPMs up to 14,000 maybe. Those kind of applications, and that's due to the low fatigue life of the aluminum. And when aluminum is used under high stress situations like in drag racing, it can be used in that kind of situation only. But they can be safely used when using daily driver for aluminum rods. Grodin and Magnus aluminum rods are usually the best choice for those kind of applications because they're really strong and really light. And finally, titanium. I don't have any titanium rods because those are extremely expensive. I don't have those laying around. Usually when I build an engine, someone wants titanium rods, they bring them to me, and I don't keep them laying around because of the cost of it. But those are used in super high horsepower applications. 1,400 horsepower, 14,000 application, 14,000 RPMs. Those are the kind of applications that those will be used in, and they can be used in daily driving, endurance racing, but usually in drag racing for titanium rods. So that's what we talk about with the different designs, materials, different machining, what you're going to do when you have it machined, what they're going to look for, how it's going to be balanced, how it's going to be put together. Now, let's put together one of these connecting rods to the piston, and I'll show you some things to watch for when you're putting together. So if you decide to put it together yourself, you'll be sure that you're not having a problem and what to watch out for. Okay, so now if you're going to assemble your own pistons to your rod, there's a few things to make sure. First of all, it's got to be extremely clean. Make sure your piston, all your assemblies are clean. I have one of these, one clip is placed already inside of this piston. And these wrist pins are designed for a slip fit, which means when you put this in here, there actually is an engineered or designed amount of force required to push this in there. And if you have to force it in there, if you can't twist that in there, there's something wrong. You want to take it to the machine shop and have them check that out. That's why I have all my pistons and connecting rods fitted at a machine shop. So I'm just going to sit my wrist pin in there, and I'm going to take my connecting rod, and if you notice the connecting rod has a bushing in there, a brass bushing or a bronze bushing. It's usually an oil impregnated bronze or just a high performance bronze, and that's usually designed for wear. And there is a direction. This particular connecting rod doesn't have a direction, so I don't have to worry about how it's put in there. But I'm going to sit this, I'm going to take this, I'm going to be very careful. I'm going to push my wrist pin up to the connecting rod, and I'm sort of going to slide the rod on, and I'm going to push this all the way in until it meets the ring or the keeper that I have on that side, which is fully in. And then now the wrist pin is fully inserted in the piston, and I'm going to check to make sure that it moves freely, make sure there's no binding, make sure it slides back and forth. You can see it slides back and forth, and there's really no slop in that. Now all I have to do is drop in this keeper, put this in the groove, which might be difficult to do with gloves on in front of a camera. But no, it's going to be a little bit too difficult. I can't do both at the same time. So you just install that keeper and your assembly is done. These keepers, these rings, and when you put these in, it is extremely important to make sure it is fully seated in the groove in there, because if it doesn't, this keeper will fall off, the wrist pin will slide out, score the piston, and you're going to lock up your engine. The engine's going to be destroyed if you don't put these in right. So use your eye loops, look to make sure it's fully seated in the groove all the way around, and you'll have a good assembly. When I have my pistons and rods assembled, I have the machine shop do it because they check the press force. They make sure that the wrist pin is not pressed in too tight so that it's not going to crack the piston, and then they make sure that the different keepers that I use that are a racing keeper, it's going to hold that ring in place. So that's the basic assembly of a connecting rod. Now I have a fully assembled connecting rod with the piston, and let's put the rings on. We'll talk about rings and the proper installation. Before we install the piston rings, let's talk about the different types of rings. You'll have a top ring, the compression ring. The second ring, a compression ring, which also acts as a wiper for the oil in the cylinder. And then you have your oil rings. The oil rings will consist of a top rail, your scraper, and the bottom rail. Now, the single most important factor when you're selecting the proper compression ring, which is the top ring here, is the face coating, the coating on the edge of the ring. It has to meet the service requirements that the engine is going to be operating under, and that's very, very important. Is it going to be subjected to unusual speed, loads, temperatures, stop and go, short trip, occasional rides, those kind of things. Even in high dust, there are rings made for high dust or dirty environments. So those are things to consider when you're choosing your rings. Three popular types of compression ring face coatings are cast iron, moly, and chrome, and each has its operation advantages and disadvantages in different operating conditions. But first we talk about a cast iron ring. A cast iron ring, they're going to be durable. It's going to have a durable wear surface under normal operating conditions, and those are the least costly than a moly or a chrome faced ring. For typical light duty service, rebuilding your engine, a regular cast ring is completely okay. It's not subjected to long periods of high speed or high load, and it's run primarily on regular streets. And a plain cast iron is a fine rod, a fine ring. Moly rings. When you have a moly ring, moly coated rings, there's slight moly coating. These have a very high resistance to scuff, and they have superior oil control. So if you're going to looking for faced with continuous or occasional high speeds, high loads, where the engine is subject to periods of high temperature, racing, that kind of thing, moly is a good choice because the scuff resistance of the ring itself and the strength. Moly, which is it's just an acronym for molybdenum or molybdenum, depending on how you want to pronounce it. It's quite porous in its applied state, which results in excellent retention of the oil in the face of the ring. So moly also has the highest melting point of the three popular coatings, which results in its capability to live longer under more of the severe operating conditions. More specifically, its resistance to scuffing and scoring. Moly rings are better suited for performance engines. This is going in a performance engine, so I'm using a moly ring. And these rings are expected to be severe, adequately expensive, not too bad. If these rings are going to see any kind of severe stresses throughout the life of the engine, a moly ring is good to go with. The last one is a chrome ring, and I do not have a chrome ring, but chrome rings have a good resistance to scuff. They do not exceed they have good resistance to scuff. It's going to be better than an iron ring, but they don't exhibit the moly's oil retention capability, the chrome ones. In a dusty environment where you've encountered a lot of dirt, unpaved roads, those kind of things, chrome is the best choice. If you're doing off-road racing, a chrome ring is going to be the best choice for you. Moly, because of its porosity, holds oil. Chrome does not. That's what's important about that. Yet the pores of the material can also serve as a trap for foreign materials. So chrome is going to be a better material if you're using it for off-road. Chrome also has more resistance to scuffing and scoring than cast iron, but somewhat less than the moly ring. So you choose your applications, and you can talk to the person you're buying it from, and I'm sure you will find they'll be very helpful in helping you choose which ring is best for your application. Now, let's put the rings on, and then the first thing we need to do before we put the rings on, let's go through gapping a ring. How to properly gap a piston ring, and how to check for that, and I'll show you what the formula is. Gapping your rings is a fairly easy process. Now, what I have done is, this is going to be my top compression rings, and you can do all your rings all at once, but I suggest gapping them in the cylinder where they're going to go. So gap it in the cylinder it's going to be placed. Right now I'm going to do number 1 cylinder in this engine. And all you do is you take the ring and push it into the cylinder, which sounds easy, like that. I have it pushed in there. And the idea is to get this perfectly straight. And the way you do this is, I have a piston here, and I installed the ring on the number 2 compression slot, or the compression groove. See that ring in there? I have a ring in there. What I'm going to do is I'm going to place this piston on top here, and I'm just going to tap down slightly to make sure it's pushed down evenly all around. And when I pull out the piston and set it aside like that, you're going to be sure that the ring is even all the way around. And here's the gap. Now, the formula, or the general rule of thumb for gapping your piston rings is this. The compression ring, the top ring, you want to get roughly 0.0045 times the bore, which is, let's say your stock bore is 3.68, 4.0, whatever. So if you have a compression ring and you're going to put it in a 368 bore, the gap in here is going to be about 16,000ths of an inch, right in there, 16,000. That's roughly the formula. For the oil wiper rings, it's a little tighter. It's 3,000ths times the bore. So if you have a compression ring, it's 4,500ths for the times the bore. Will give you 16,000ths, and the oil wiper ring is 3,000ths times the bore, which will give me roughly 11,000ths. And I've already gapped these rings, and these rings are already gapped properly. Now, if you're going to gap them yourself, and you have to open that up, well, you have to make sure that you grind. Let me pull this up here. Take this ring out. The critical thing about gapping a ring is making sure that you grind the end of the ring perpendicular. You don't want to do it with a file and make this rounded. You want to make sure that that end of that ring is nice and square. Very, very important. So that's how you gap your rings. Now let's install the rings to the pistons. Show you the right way and the wrong way. Now let's install some piston rings. Before you get started with installing your rings, you have your rings laid out. You make sure you have the orientation correct and things are ready to roll, and you have your rings, the grooves, nice and clean. Before I install a ring, I like to give it a turn the piston around. Making sure the ring grooves are clean, because if you recall, I was talking about FM. FM underneath the ring is just as bad as FM on top of the ring. Now I'm going to show you the A way to install the rings, and then I'll show you the wrong way and why it's the wrong way. First, I'm going to start with the oil rings. I'm going to put the oil bottom rail for the oil ring on first. And these are very, very flimsy. The oil rings are going to be very flimsy, so you can sort of sit it in the groove, bring it around, and there's one thing you have to be careful. As you bring the oil ring around here, the oil rail, and you get it in the groove, this is what I'm going to show you. Now, I'm not going to do this, but when you get to this point, when you bring this corner of this ring over the piston, the edge of the piston here, if you just drag it over the edge here, it's going to leave a scratch right here, and that's a leak path. Pull the ring, or pull that bottom rail out. It's pretty flexible, so pull it out away from the piston so you're not going to scratch the ring. You're not going to scratch the piston. You're not going to damage the ring. And make sure it's in the groove all the way around. And you can see I have that in the groove all the way around, just like that. In the wrong ring. I have it in the wrong groove. It's tough to make videos and do this at the same time. So let me just move this down. One groove. Just like that. And I'm going to lift it up to make sure it doesn't scratch. Okay, now I have my bottom rail in. I'm going to take my wiper, the wiper for the scraper for the ring. I'm going to take my gap for the oil ring. And these are not orientation specific, so you can just slide this on. And I will go all the way around with this one, making sure I don't scrape it, and lift it up. Set it in place. Just like that. Make sure it's on top of the bottom rail all the way around. Now that I have that seated in there, I'll take my top oil wiper, set it in the groove, bring it all the way around, and lift it up so it doesn't scratch the edge of the piston. So now I have those installed. We'll talk about orientation of the gaps when we put them in. Now, the second ring, the second compression ring and oil wiper ring, always follow the manufacturer's recommended way to install the rings in the orientation. Most piston rings are going to have a dot. Right here's a dot right here. I think you can see that dot. That dot usually faces up, but that's not necessarily the case. But always follow what the manufacturer recommends about the orientation of that dot. Now, you could put this on here, slide this ring around the piston, but when you get, these rings are a little more brittle. The compression rings are more brittle, so and they're thicker. So when you get to the end, if you have to expand that to put that in the groove, these will crack. And when you crack a ring, you're going to be upset, and you have to buy a whole new set, and you can't get one or two. So I like to sit the ring right on top like this, make sure I have the correct orientation. Then what I'm going to do is I'm going to take a pair of piston ring pliers, and this makes it very easy. All you do is you take it and put it in the gap of the ring like this, and what it does is it opens up the ring so you can slide it right over the piston, right into the groove, and it works beautifully. Seconds. I did that within seconds, and I didn't destroy it. Same thing with the top compression ring. You're going to take the top compression ring, look for the orientation dot right on top there. You can see the orientation dot. Always goes towards the top. I'm going to hold this ring right like that and put my ring expander in there, pull it over the top of the piston, slide it down to the groove, and I missed it. See how I did that? I missed it. And I don't want to try and expand that, because if I do, I run the risk of cracking this ring. I don't want to crack a ring. So I'm going to just sort of pull this out of there, and I'll do it again. Take your time. I'm going to go open it up, put the ring over the groove, and release, and there. Now I have all my rings installed in all the grooves, and right before we put this in, we'll talk about the orientation of these gaps, because there's some myths about that and some truth to some of it, so we'll talk about that when we put this piston in. Before we do that, let's talk about fasteners, connecting rod fasteners, because that's going to be done right when we put the whole thing together. Now we're ready to install the pistons, but before we do, let's talk quickly about the bearings and the connecting rod bolts. I talked before about cleanliness of bearings, and the cleanliness is extremely important. You want to make sure that there's no FM underneath the bearing, so when you put the bearing in place, there's nothing underneath it, and no FM or foreign material on top of the bearing. That's very important. The next is going to be your selection of bolts, and I use ARP bolts for all engine builds, and I have before referred to ARP bolts as grade 8 hardware, and they're actually more than that. They're actually better than aerospace quality bolts, because ARP puts a great deal of thought into their fasteners. And I'll just go through this really quick. They offer very, very different kinds of fasteners for different uses depending on your application. They offer a stainless steel bolt, and these are suited for most automotive and marine applications, because stainless is tolerant of heat and virtually improves rust and corrosion. And it has a good finish, and the tensile strength is around 170,000 psi. You can also get a chrome moly ARP fastener, and until the modern alloys were made, chrome moly was popular because of the high strength of the material, and the moderate strength of an 8740 chrome moly is seen as a good steel with adequate fatigue failure properties for most racing applications. But it's because of the heat treatment and the way they do it, and typically a chrome moly is classified as a quench tempered steel, and it can be up 180,000 to 210,000 psi for a fastener. And again, recalling that most of the failures are caused, most connecting rod failures are when the bolts fail and the bottom cap falls off the rod as the engine is under the compressive load. They also have a material ARP 2000, which is an alloy steel, and it's heat treated to a higher level. It's a greater strength than the 8740, and it can have compressive loads up to 220,000 psi. They also make an L19. The L19 is considered to be one of their premium materials because of its high compressive strength, and it's a premium steel. And L19 is a very high compared to the 8740 and ARP 2000 that can go up to 260,000 psi. They also have a material called Aeromet. Typical tensile strengths of 290,000 to 310,000 psi. That's a super alloy because it's strong. the austenitic material or the austenitic design of the fibers or the structure of the granules of the steel make it extremely strong. They also have a Inconel. Inconel is something like chrome moly rod, and it's a nickel-based material, so it's a little different than the other materials, but it's a super alloy class. Inconel can be from 210,000 to 230,000 psi because it has improved fatigue properties, and best of all, the Inconel, the 718 that they make it out of, is completely immune to hydrogen embrittlement and corrosion, so that's why they use that. They have an ARP 3.5, which is an AMS 5844, similar to Inconel 718, but it's a super alloy that's usually found in jet engines, aerospace applications, and it'll have a tensile strength of 260,000, 280,000. And that's immune to hydrogen embrittlement and corrosion, and these are usually NASCAR and really heavy-duty racing applications. They have a custom-age 265 plus material, and that's a newly formulated super alloy. It demonstrates a superior fatigue cycle life, and tensile strengths of that usually go up to 260,000 to 280,000 psi. They also make a titanium fastener. Titanium fasteners, again, going to be lighter. It's an alloy. It's a titanium 6 with aluminum, and it's got some chromium in it that's specially treated, and it provides superior strength to other titanium alloys in racing and aerospace application, and this has really nominal tensile strengths for 180,000 psi and is very corrosion resistant. The advantage of a titanium fastener, if you're going to want to reduce the weight of your engine, a titanium fastener can be about 40% lighter comparable to a fastener made out of steel. So head studs, accessory bolts, rod caps, those things are going to be ideal applications for the lighter weight material. So those are different materials that you can get connecting rod bolts made out of, and those are the ARP fasteners. Those are the ones I like to use. So we have that assembly there. Now before we put the piston together, or before I install it, again I just want to talk about the materials of the connecting rod bolts, making sure that your bearings are clean on both sides, cleanliness, and that you have everything lined up, ready to install. I have this backwards. It actually goes in this way, and I'm going to sit this here, and we'll align these rings, and then I'll show you how to put this into the cylinder. Before I install the piston, I'm going to turn the crankshaft to make sure the pin is furthest away at bottom dead center. I want to do that so when I put the piston in, when I push the piston in, I don't run the chance of nicking that pin. Don't want to nick that pin. You nick that pin, you got to take the crank out and have it reground. That's number one. Now let's talk about, let me go to the piston orientation and compression and installation. Okay, now let's install one piston. First, before I start, I have the bore lightly oiled with some 5-weight oil just to help with the installation process. I have a light coating of assembly lube on the bearing. I have a rubber band around the bottom of the connecting rod to make sure when I put it in, none of the corners will make contact with the cylinder bore, causing a score, nick, or scratch. Very important, especially if you have bolts that are installed to the rod. You want to put some sort of rubber protector or some sort of plastic cover over that so the rod doesn't nick anything on the way down, especially when you push it down into the cylinder and it gets to the pin on the crank. You do not want to nick the pin on the crank. So the orientation of the piston is going to be this direction. I have my rings, the orientation of the rings per the manufacturer's instructions, and always follow the manufacturer's instructions on where to put the gaps. I have my gap here for my top ring, top compression ring, bottom compression ring, top oil rail, bottom oil rail, and scraper for the ring. Now, it's as simple as I have my ring compressor here, and you open up it's just going to be tough to do, make a video at the same time, but let me see here. I'm going to open this up. Now I'm doing this without gloves on just to make it easier because it's a lot easier to do when you don't have gloves on. Now you place your ring compressor over your piston, and you want to leave a little bit left on the bottom here so that you can get it lined up in the bore. I like to start to turn it just to get it a little lined up, and it's just a matter of cranking it down to 1/4 inch. 1/4" ratchet, making sure it's on there nice and square. Got to be on there nice and square or else the piston won't come out straight and the rings will expand and lock up. Now, what I'm going to do is, let me take this off. Let me just make sure it's tight. It's got to be relatively tight. One last click there. Get the orientation correct. Sit it in the bore here, and I'm just going to get those skirts lined up with the piston just like that. Now it's going to be straight. Now, you want to push this in and try and get it in one continuous motion. You probably won't do it. You probably have to tap it a couple times. But if as you're tapping it down, if one of the rings pops out underneath the ring compressor, stop. Because if you hit it again, you're going to crack that ring. Hopefully that doesn't happen here, but I'll give it a shot. I take a rubber mallet and I put it on the top of the piston, and I want to make sure it's square. I'm going to hold it square, and I have another rubber dead blow mallet here, and I'm going to hit it, start tapping it in, and when I get towards the bottom, I'm going to wrap it pretty good. And my ring compressor will fall off. My piston is installed, and now I can reach underneath. I'm going to reach underneath here to make sure I don't hit the pin. I'm going to make sure I push this down. I'm going to grab the rod underneath. I'm going to take off the rubber band that I put on there. I have that girdle underneath there, so that kind of creates a little bit of a problem for me. But I have the rubber band off. Now, I'm going to put my hand around the crank to make sure I don't hit that pin. I'm going to push this down slowly and push it right to the connecting rod. Now what I can do is I can flip this over. Take and turn this over. Make sure I grab something here. This tool over here. It's tough to see with the girdle there, but my piston is all the way down. I can take my cap, my piston, my connecting rod cap. I will put a little bit of lube on my cap, like that. I will make sure I have the orientation correct. And be very careful not to touch the crank so you don't nick it. And that will push right in place. I'll slide this, turn the crank around. Put my rod bolts in place. Now we'll tighten these down. I'm not going to torque them down yet. I'm just going to tighten them all down. Now I'm going to continue and put all the 8 pistons in, and we'll come back and measure the clearance for the end play, or the clearance between the rods and the crank. I wanted to stop and show you what I was talking about. If you go to put pressure piston in here, and one of the ring pops out like that, you want to stop, because if you continue, you'll crack that ring. You got to pull the piston out, go through the whole process, and make sure you have all the rings inside. That happened because this piston compression sleeve got a little off-centered, it was a little crooked, and the ring popped out. Stop immediately and fix that. Start all over again. Now all my pistons are installed, and I'm using an SRP forged piston, part number 206061. These are RPM I-beam race rods with the ARP 2000 bolt upgrade, torque down to 62 foot-pounds. And what I want to do is I want to check the clearance between my connecting rods. So what I'm going to do is I'm going to go in between my connecting rods. This is 3/1000. 3/1000 goes in there fairly easy. And now I'll check it with the 4/1000. And the 4/1000 does not go in. So I have between 3 and 4/1000 connecting rod clearance, and there's 3 separate, 1, 2, 3 separate gaps there. So it's about 1/1000 per gap, which is ideal for this engine. Now I'm going to turn it over and we'll do one last torque check. Now, in order to check your installation of all your pistons, there are 2 kinds of torque you need to check: the breakaway torque and the running torque, or the rotating torque. And it's pretty difficult to check you have to look at the engine that you're building and check what it is. It might be hard to find it, but it's really worth looking at. And the breakaway torque is how much torque does it take to get the crankshaft moving, to get the pistons moving. That will tell you how much resistance or how much friction there are from the pistons and the bearings and the rods, and if you have any interference. Then there's the running torque. How much torque does it take to keep it moving once you get it moving? And that'll let you know, once you overcome the initial friction of all the rotating assembly, what does it take to keep it running? And you could sort of feel it. If you just break it away, you'll feel the breakaway torque, and as you turn it, you'll feel it drop. Breakaway torque and then running torque. And then what you want to do is turn the engine over a couple times, very slow, to see if you feel anything very tight on any of the pistons, or see if you can hear anything grinding or it doesn't sound right. Just turn it over once. You don't have to do it too many times, because if you do, the oil you put inside the cylinders is going to wipe off and you're going to create friction. So just turn it over, make sure everything works free and nothing's making noise, and you should be all set. So there we have pistons, rings, rods, and installation. And if you're thoroughly confused, you're not alone, because so am I. It is a lot of information, and don't be afraid to consult professionals and ask for help. Make sure you engage your machine shop that you're going to be using throughout, so they help you choose your parts. And picking your pistons, picking your rods, picking all your parts, it's all part of the planning procedure. You should have this all picked out before you even start building your engine, so you have an idea of what you want your engine to do. Everything from the block, crank, bearings, pistons, rods, cam, the whole shot, everything should be chosen before you even start. If you have any questions, send me a text. I'll answer it if I can. If I can't, I'll find someone who can answer it. And you can also send me an email if you'd like, if you have a more lengthy question, and I'll help you if I can. I really appreciate you watching, and I hope this helped you. Thanks for stopping by Pete's Garage.